Now, time to discuss some of the reactions of aromatic compounds. These compounds undergo what are described as substitution reactions. In a general sense, those are shown to be two reactants that each have two parts. A and B are reacting with C and D, and the result is that A recombines with a portion of the second molecule, and C recombines with a portion of the first molecule. So some group is substituting for a ring hydrogen. In this case, this shows as the hydrogen on the right side being replaced with a Y atom. So the Y goes on to the ring, and the hydrogen goes to X. And so you're having a replacement, a substitution of what is connected to the ring, and the displaced atom goes connected to the other half of the reactant molecule. Specific types of reactions in this substitution category are characteristic for aromatic compounds. Only certain ones are common, and those are the only ones that you need to be concerned with for this purposes of this course. Each of them has a separate name, but they're still all substitution reactions, and we'll look at them each in turn. The first is nitration, where you put a nitro group on the ring. Nitro is what the substituent name will be called in this case, and you use nitric acid to do it. How about that? And so you're substituting the hydrogen with an NO2. The displaced hydrogen then combines with water, with OH to make water, and the product is called a nitrobenzene. This reaction requires a catalyst, that's sulfuric acid, but I won't try to trick you about that. It's just to know that they won't react without some encouragement. The catalyst is required. So there's the nitro substituent on the benzene from this example. Yes, substitution reaction because you have two reactants and two products. Sometimes we forget about the second product, but we should be paying attention to them. So nitration is substitution variation number one. The second one is called halogenation, where you use X, namely any of the halogens, which always comes diatomic. So you put one of the halogens in place of the hydrogen on the ring, and so the halogen going to the carbon, the displaced hydrogen goes to the chlorine, and we have a chlorobenzene, or we call it a halobenzene, which is a generic way of saying it, a halo product. And nothing more complex, but we do still have the HCl leftovers. This is exactly the same idea as what we saw with halogenation of alkanes, where there was a halogen halide. That's what we call that, a hydrohalogen, or, when you're left over. So those are acids that are left over, but we've seen that already with alkanes. The third variation is called sulfonation, where you're putting on a sulfonate group. And these are the funniest ones to name, so don't really expect to see any specific ones testable on this. But sulfonation uses sulfuric acid and SO3. Let me back up one moment. I didn't comment here. You do require a catalyst. The catalyst of some type, iron can be used, or aluminum chloride can be used for the halogenation reaction. I forgot to state that. The sulfonation reaction uses sulfuric acid again as a catalyst, and this is shown kind of in wishy-washy ways because sometimes the SO3 is shown as a catalyst and the sulfuric acid as a reagent. Whatever the case, you have to have them together, and it's a question of how you think about them. Personally, I think I'd like to think about them the opposite way, because you can't see this as two parts losing something. So if you think of the sulfuric acid as HO and then SO3, does that come out to be the same? I believe so. And then if you take the SO3, whoops, I forgot one more hydrogen, there you go. If you take the SO3H and use it to replace the hydrogen on the ring, then the hydrogen goes to the OH, and you get water as a byproduct once again. So you get sulfonate derivatives. Again, it's substitution. I should have made the arrow go here. And the substitution leaves a second product of only water, and sulfonate derivatives are just one of the kinds of examples of these three characteristic types that you can have for aromatic reactions. So let's try some examples with specific benzene derivatives rather than generic ones. So the first one, we're going to react with bromine, and an iron catalyst. Without the catalyst, it would just kind of sit there and wonder, and you wouldn't get much. So let's put bromine in here and assume the iron catalyst. CAT means catalyst. And let's draw the product. Now you're going to know about this soon if you haven't heard it already, that I will try my level best to never show specific multiple bonds in that six-sided ring that we call an aromatic compound, because they don't actually occur, and it's deceptive. What we see represented here is OCH3 on the left and OCH3 on the right. Pardon my having those a little so close together. Now, what we have to substitute here is going to be one of the hydrogens on that ring. There are only 4, so only those places can possibly have a reaction. So let's put the bromine here, and we don't really care for the moment. Let's just start that way. And that means that you will have a displaced hydrogen combining with the leftover bromine. And are there other possible products? This is what you always have to think. In this case, there really is only one, because if you put the bromine on the next carbon or the other 2, substitute for those other 2 hydrogens, you're always going to have the bromine one position away from that OCH3 group, which is actually an ether, just in case you hadn't thought about it, the ether group. And whether you put it on any of those 4 places, the product you get when it's only reacted one time looks precisely the same. So here, 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 and here will always be one position away from the OCH3. Now, looks simpler than you might have imagined. Let's try the second example, where we have the sulfonate derivative generated by reaction with SO3 and a sulfuric acid catalyst. And as I told you, which one is the catalyst and which one is the reagent is sort of arbitrary, because both have to be present. And in order for these to make sense, let's try not to make them worse than necessary. We'll think about this. Oops, sorry about that. So we'll draw the original compound and decide where on here the substituents will go and how are they going to be different. Again, you're going to be replacing one of the hydrogens with the SO3 group. So think of it as sulfuric acid as being SO3H connected to OH. And if so, this time let's pick one right here. We'll put to take away the hydrogen and combine it with OH to make water. And then we'll put the SO3H on the ring. Again, it's adjacent to that ether linkage that is on the benzene ring. And we don't have to worry about naming these. That's entirely too much to worry about at this point in the game. Whichever one of the hydrogens you might have selected, the product you would get would be exactly the same, as long as you're only putting on one new group onto the ring. This would be like other cases where you can't exactly keep it controlled and limit how many possible products there are, but it gives you the idea of the fact that 4 different carbons give you the exact same product in this type of reaction. All right, with substituents on the ring, things become interesting, and you pay attention and find out that there are fewer possibilities than you first imagined. All right, I hope you find this helpful. Keep working hard on the homework, ask lots of questions, and I'll see you in class.